the derivative as tangent vector. To motivate this video, I want to talk about things going on in one-dimensional space, just, y is a function of x. So suppose that we just have y is equal to x squared minus 4. And I guess really when I say one-dimensional, I'm going to draw a graph here in 2 dimensions. What does the graph of x squared minus 4 look like? Okay, it looks like that. And if I ask you to find the derivative of this, dy dx, of course this is very easy. Problem dy dx is equal to 2x. So, classic Calc 1 problem, find an equation for the tangent line at x is equal to 2. So when x is equal to 2, we plug in 2 here, we get y is equal to 4 minus 4, y is equal to 0. And when x is equal to 2, dy dx is equal to 2 times 2 is 4. So an equation for this tangent line right here, this red tangent line, is going to be y minus our particular value of y here, y naught, is equal to the slope, which is the derivative 4, times x minus x naught, x minus 2. So this is, classic Calc 1 problem, finding the equation of this tangent line here. But now let me rewrite this in a way that is more evocative in a Calc 3 setting. So namely, let me try this. I'm going to write this as r of t is equal to t, comma, t squared minus 4, comma, 0. So observe here that if we take this xy plane and put it into 3-dimensional space, this is a parametrization of the same curve here. So the z component is 0, because we want the z component to be 0. We want to stay in the xy plane. For whatever value x is, that course, t corresponds exactly to x, and then y is going to be t squared minus 4, but t corresponds exactly to x. Y is equal to x squared minus 4. Okay, so let's see if we can do all of the same stuff here that we just did using this setting. So let's take the derivative. R prime of t is equal to 1, comma, 2t, comma, 0. So that would be the derivative of r of t. And let's evaluate the original vector valued function here and the derivative at 2 times t is equal to 2 for the same reasons we want this to match over here. So r of 2 is going to be 2, comma, 0, comma, 0. And r prime of 2 is going to be 1, comma, 4, comma, 0. So we have, observe here, that what we can do is that we can write the following. L of t is equal to 2, 0, 0, plus t times 1, 4, 0. Why does this kind of make sense here? So this right here, this corresponds to a point on the tangent line. And this is a direction vector for the tangent line. Tangent line. So right here, again, thinking of this in 3-dimensional space, I'm not drawing the 3rd dimension here, but the point 2, 0, 0. And going in this direction, if x increases by 1 unit, y increases by 4 units, z doesn't change, that sure seems like a slope of 4 here. So the vector 1, 4, 0 is pointing in the direction of our tangent line. We have a position vector for a point on the line. We have a direction vector for our tangent line. It's very easy to combine those two pieces of information. It's very easy for us to combine those two pieces of information here to get an equation for the tangent line. So what's going on here? Let's kick this up more generally speaking. Let me write the following fact. R prime of t naught is a vector that points in the direction tangent to the path of r of t at t is t naught. And so the particle we're thinking about, this particle moving, is at r of t naught at time t naught. So our tangent line, generally speaking, L of t is r of t naught plus t times r prime of t naught. And this will give us, let me just draw, we have, okay, something moving around in three-dimensional space here. At this point, if this is our time t naught, this would be r of t naught right here. That vector would be pointing in the direction of r prime of t naught. And we could use that information to draw the tangent line. Okay, so let's do a three-dimension specific example here. Let's find the line tangent to r of t is vector t squared t minus 1 log of t at t naught is equal to 1. So what information do we need? We need r prime of t. Take the derivative here. We get 2t, 1, and 1 over t. R prime of 1 will be 2 times 1, 1, and 1 over 1. And let's not forget that we need r of 1 itself. So that would be 1 squared is 1, 1 minus 1 is 0, log of 1 is 0. So take these two pieces of information. Our final answer here, L of t, is 1, 0, 0 plus t times 2, 1, 1. So this is how you use the derivative to find the equation for a tangent line to your curve. So I think this is a pretty important problem type. So here is a pre-class problem for you to do. So find parameterization for the tangent line, very similar thing to what I just did. Here's the parameterization when t is equal to when t is equal to -2.